Okay, so we are very happy to have Amos with us today. Amos is starting or very recently joined as a postdoctoral researcher in Australian National University. Amos works on, as I gather from his online persona, he works on reactive systems with high assurance and has been using model checking to do so, but recently started using a star or at least made a demo that he posted on Slack uh, of using a star to verify some reactive control systems. So, Amos, over to you.
Yeah, so I was, until relatively recently, I was working at this autonomous vehicle company, and we were using model checking to verify some properties of the really safety critical stuff, like the most critical bits which interface directly with the car, which are always on, even when the system is not self-driving. That's an even higher level of criticality than like the driving decisions that you make. So we wanted to make sure that they were sound, that we could trust them. So I want to spend a bit of time on more the motivation for why we want these sort of things, or the sort of properties we want to state. So a really interesting, I think, example of a safety critical system is anti-lock brakes on a motorcycle. So we've had anti-lock braking has been around for 50 years, maybe more, but it's only started being really applied to motorcycles in earnest pretty recently. So the idea is that when you're moving and you start braking, at a certain point of squeezing the brakes too hard, your wheel will lock up, and it's easier for the wheel to slide than it is to stop the bike and keep rolling. So this is bad in a car because you lose control of the direction you're going in, but it's even worse on a motorcycle because you only have two wheels and you rely on the rotation of the wheels has a gyroscopic force that keeps you up, right? So if the wheels lock up, you become very unstable. So I think it's an interesting domain from that perspective, at least. So the rough idea of a anti-lock braking system, or the rough idea, the rough design of an anti-lock braking system is that you have some wheel speed sensors. These are the omega front and omega rear on the motorcycle there. And they tell you how fast the wheel is actually spinning. But to figure out whether the wheel is locked, you need to know how fast the vehicle is actually going. So to get that, you need to estimate the vehicle speed. So one technique is to get an accelerometer, which gives you the acceleration and braking. And you can use that to get an idea of how fast the vehicle is going. You can combine these things. And then using that, you can compute the wheel slip, which is the speed of the wheel divided by the speed of the vehicle, inverted or something. But that tells you how bad the wheel is locked up. And then you can use that to control to release the brakes. So an example of how we might implement just the vehicle speed estimation. Well, suppose that we want to write a function that updates our vehicle speed estimate. it takes the omega front and the omega rear. So these are the two wheel speeds, actual wheel speeds. And it also takes the accelerometer value, and it takes the previous estimate of the velocity, vehicle's velocity. And we assume that this is called every 10 milliseconds, 100 times a second, and returns a new updated upper bound. So this is a little bit, we might imagine that we could just integrate the accelerometer, but there's a lot of error is going to accumulate. If you're driving for an hour and you're integrating an accelerometer value over an hour, you're going to get really bad results. So the basic idea is to instead compute both of the wheels, the corresponding vehicle speed from the wheel speeds. So we just do that by multiplying by the circumference, and that gives us VF and VER. And we say if the two wheels are rotating at roughly the same speed, then that's probably the speed of the vehicle. If they're going at the same speed, the wheels probably aren't locked up, and we can trust that it's a good estimate. Otherwise, if they're not the same speed, probably the wheels are locked up or something funny is happening, and we should just integrate. Start taking our previous estimate, add the accelerometer, and add a little error margin just to quantify the uncertainty. Forgot to mention, please just yell if there are questions or whatever. So this is, I think, a reasonable first implementation. So with our implementation, we probably should have done it first, but now we want to think about how do we gain confidence that our implementation is correct? What properties should our implementation satisfy? And one nice property, one trivial property, is that if the two wheels agree, then the estimate is pretty good. And we can prove this. It's very easy because it doesn't require induction or anything. It's just falls out straightforwardly from the if condition. So that's okay. But hey, it would be nice to quantify how bad the error deteriorates over time. And me being the way that I would think to naturally express this is with some sort of temporal logic, with a temporal argument at least. We want to say that if the wheels agreed within the last minute or so, there should be a bound on how bad the estimate is, because it's only been integrating for a minute at most. And we can express this as a linear temporal logic predicate with this filled diamond. So ordinary diamond is finally or at some point, but the filled diamond means previously, past time. So at some point in the past, the wheels have agreed, and this subscript t means that it's within some time t. So if the wheels have agreed within time t, then our estimate is bounded by epsilon times t epsilons. So I think this is, intuitively, I think this is a nice property, but it's not easy to state on our implementation because our implementation isn't talking about time at all. It's just one step of the update. So we would need to restate this as some sort of iterate or fold over over a bunch of inputs, and it would, I think, lose the clarity that our nice temporal property has here. So this update function isn't so hot. It's not so great. So what can we do instead? The idea is to instead encode our programs as reactive systems that have an innate sense of time, a sense of time and the progression of time. So our program was too low level before. We couldn't state the properties the way we wanted. Now we want a slightly higher level of abstraction to be able to state the properties. So if we rewrite it as a reactive system in this Lustre style syntax, we would say we've got a node, and let node means that this is a streaming computation rather than a pure or instantaneous computation. And most of it remains pretty similar. The computation of the front and rear velocities is the same. It's just lifted to the streaming level. So omega f is a stream of values here rather than a single integer, but the operations are implicitly lifted over strings. Then the interesting part is this let rec, the v hat, the new upper bound of the estimate. We say if the two velocities agree, then it's the minimum of the two velocities. Otherwise, it's the previous value of the velocity, so the previous estimate, plus the accelerometer minus the epsilon. But if there's no previous value, like at the very start of computation, we need to initialize it with just the minimum value. So this is how we would express our original estimate program as a Lustre style program. And yes, do you have a question?
Yeah, it looks really interesting. I'm not familiar with Lustre very much at all. So my question is about this pre-operator. Like, how far back in the stream are you allowed to look?
So it's a statically bounded amount, really. It's so in this case, it's the execution assumes that there's a step function that's executed, in this case, every 10 milliseconds, and pre looks back one tick, one instance. But you can say pre of pre of pre, for example, but it needs to be. The nice thing about this limited language is that it ensures that it requires finite buffer, finite memory to execute. So to do that, you really need to have a finite bound on how far you can look back.
Okay, yeah.
So with this, we can so one of the other nice thing is that we can state properties of this. So we can just state properties which are in the specification language of Lustre. They are just expressions that are true. So most of the model checkers don't have a. That's not true. Some of the model checkers have quantifiers in the predicate language, but they're quite limited. So most of the time you can. I've clouded it. we can just pretend that the predicate language is the same as the expression language for now. It's just Boolean expressions, really. So the nice thing about this particular property that we're checking here, we're checking that if the two velocities agreed within the last t time limit, this is a property we can state and prove, but it's also an expression that we can use at runtime. So this is useful for implementing like fault detection, for ensuring that the hardware is well behaved. We can write properties that the hardware should satisfy and check them at runtime. So we have a relatively weak predicate language, but that gives us some power in some sense, which I think is quite interesting. So I call this Pipit because for no real reason. Pipit is an Australian bird, and then a couple of weeks after naming it and working on it, I saw a pipit for the first time and photographed it. So I was happy about that. So that's why that's the motivation for why we want to have these sorts of programs, and why we want a domain-specific language for this purpose. It's a nice domain where we get a lot of power from having a very weak language. So I really enjoy that aspect of it. So I'm working on an embedding of this Lustre style language in F-star. And the idea is that it's a little syntax, a little library of definitions, and they desugar to a deep embedding of a ASD of a core language. And then to verify the properties that the properties hold, we translate to a transition system, a labeled transition system, and we can prove things k-inductively there. So the reason for this is that the semantics of the language itself aren't the best for proving properties. They're nice for understanding the intuition of the language, but they're not the nicest for proving the property.
Amos, I have a question.
Yes.
So is there any restriction on the temporal logic formulas that you're targeting, or so for example, the formula you showed us was about one step, like in the last step, if the velocities are nearby, then this thing holds. So is there a restriction on this formula? We're talking about general temporal logic.
We can't express all temporal logic. We can translate, I believe, all of past time temporal logic into expressions in Lustre. So what I actually didn't show, was the definition of that filled triangle operator, which is just a counter that says how long has this thing been false for, and if it sees that the predicate is true, then it sets the counter to 0, And if it's false, then it increments the counter. And then it really just checks that, well, that's the last time I saw a true one of that. Check that the property is, check that the count is less than 40 or whatever your time is. So. But yeah, so these temporal operators aren't baked into the language. There's something we can write, which is a nice thing, I think. So we have a transition system. That's what we prove on. Then we can generate imperative code, very, very stylized, very simple imperative code. Excuse me. So the imperative code is very simple because we usually have very simple types, and there's no unbounded recursion. There's no recursion in the language itself on the on a single step. Sorry. My voice is gone. Okay. But we can generate LowStar code, and then we can generate C code from that. So the core language, so the core language, we have values, and the semantics for it, there's that under a history of streams, big sigma. Oh gosh. I'm not sure what happened to my voice. So the value rule says that under a history big sigma, which is a sequence of stores, little sigmas, if you want to evaluate the value v, then you get v. If you want to evaluate the variable x under a sequence big sigma, followed by the current store, the most recent, then you just look it up in the most recent store. And the semantics for the pre-rule, pre-form, says if you want to evaluate pre under a sequence big sigma followed by little sigma, then just evaluate E under the previous one. And this followed by is like, or the then arrow says that if you're at the very start of computation and you've only got one stream element, then you evaluate the left-hand side, but otherwise you evaluate the right-hand side. And this mu is for recursive definitions. So you just unfold the recursion. And let is standard. And check just checks that the property is true.
Sorry, can you go back to that the previous slide for a second? The check rule doesn't mention P at all. Is that intentional?
Oh, yes, sorry. P is just a string. The intention is to use the P to say which property failed. Sorry. But I need
So,
to.
is it true that this check rule means that you encode like safety but not liveness properties?
Yeah, that's right.
Okay.
Yeah, so it turns out that liveness properties aren't in embedded systems like an anti-lock braking system. We aren't very interested in liveness properties because we can always, I shouldn't say always, but most of the time we can encode them as bounded liveness, which is safety, right? It's like the system should eventually be ready to break is really, it should be ready within 100 milliseconds. So I think, yeah, it's a very limited domain, but I think it's an important enough domain that we can make this optimization. So we have that core language. The other moderately interesting bit is that we need some way to encode this, write programs in this core language. So we have a deep embedding in F-star. And I've defined this stream of alpha type, which takes a fresh name supply and returns an expression of A, expression of alpha, and the updated name supply. But it's not a monad. The interesting thing is that it's an applicative functor, so we can map over it and we can combine two streams together, but we can't do a monadic bind. And that ends up being a little bit annoying in some cases, because if we want to do like if then else on 3 streams. Okay, if then else is actually a slightly wrong name because it's really a select. It's taking 3 streams that are always evaluating and just choosing which one to take the value from. So we can implement this if then else combinator, but it's a little shaky because we can't reuse because it's not a monad, we can't reuse the F-star effect system stuff, as far as I'm aware. But the actual embedding of the other primitives is not too bad. We can embed the pre operator is fairly simple, and it just takes a stream of alphas and returns a stream of alphas, and then combines 2 stream of alphas together. Another bit where it gets a bit janky is bindings. So because we don't have monadic bind, if we want to introduce bindings on the core language level, we need to use a specific combinator for that. It says, if you give me a definition of alpha streams a function that takes alpha streams to beta streams, then I'll introduce that binding and give you back a stream beta. So the let prime probably don't need in practice, but the rec prime for introducing these recursive streams, we do need. So if we take our idealized program from before, which is in like a lucid synchron syntax sort of, we translate that to how it actually looks, it gets a little bit messier. I don't think, no, it's not the worst, but it's a little bit messier. So we end up needing to use this if then else combinator for all of them, and these let primes. So it gets a little messy. And the pair construction at the bottom is kind of interesting too.
And where
So,
does bounded recursion come in?
sorry?
You mentioned that all recursion is bounded. Where does that come in here? We have there's a check called causality check, which sorry. So the recursion I'm talking about here is recursion as in referring to previous values of the set of a stream. It's not recursion like in a function, in a fixed point function. So here we can say we have the recursive binding of v hat, and it can refer to v hat inside the definition of v hat, but there's a syntactic check that makes sure that v hat is always referred to with a pre on it, because if you said, find me the recursive v such that v, it's not well formed. Yep, makes sense. Thanks.
They call it the causality check. So there are a few problems. Not a monad. We need this let prime binding everywhere. There's no if then else syntax, and there's no example here, but in the real code, if you say 100, you need to wrap that in a pure or something. You need to explicitly wrap it. I think the first problem with the let primes, I can just fix by doing common sub-expression lamination. It seems like going to a normal form and doing CSE would clean that up okay, I think. With the if then else syntax, I was wondering whether some sort of arrow notation, like Haskell has a proc notation for arrows. I wonder whether that would be I wonder whether that would be an interesting thing in F-star. Like, it looks like the effect syntax is already fairly flexible. I was wondering whether you could define an effect without bind, but with compose and first and second, and have it do that magic. I don't know. I also don't know whether there's any support for implicit conversions like coercions. I haven't looked very closely at the high class machinery, or whether that's relevant there. So I think there's some interesting work to do in the future. So what I have proved so far, I mean, on the meta level, on the meta level, what I proved so far is that the translation from the core language to the transition systems is sound, which tells us that anything we prove on the transition system applies to the big step semantics. However, that was on a previous version, and I've changed the semantics and added new features to the language. So I think that it still holds, but I gotta update it. I would like to prove that the imperative code gen, so I go from the core language to an imperative step function, basically. I would like to prove that is true, that it preserves semantics, because then we'll have that anything we prove actually holds. And I want to do, I think that I'm having trouble coming up with, so I worked at this self-driving car company. I'm having trouble coming up with nice critical, safety critical examples that aren't self-driving cars or that aren't motorcycles. That I think the motorcycle would be an interesting case study. Yeah, that's kind of what I'm thinking at the moment. That's what I'm planning for the future. I think that, so I just started this postdoc a month or so ago, or a couple of weeks ago. I want to write, there's, I guess, you know, Tidy, which is co-located with ICFP. I don't think I have time to write a paper, but I want to submit an extended abstract on that. And then, yeah.
Thanks, Amos. Are there any questions?
I have a bunch of questions.
All right, go
Oh,
on.
sorry,
No,
you can.
Good. Josh, go first.
I've done a little bit of thinking about Lustre for reasons that are not motorcycles, but so like one question I have is about this check predicate.
Yep.
So when you are working in a system with multiple clocks, and you have like a real-time guarantee, how does that work out? Because like the check predicate is like within a single stream, right?
Yeah. So the semantics of the check predicate is that whenever it is true, whenever the value is available, that stream evaluates true. In terms of interesting clocks, for the sort of systems I've been looking at, they usually have fairly simple static clocks. Or they are sort of hierarchical clocks, like in a state machine, where you can go to different states that are enabled, but you almost always have a super clock on top that looks at which clock is enabled and takes the value. So I guess for real-time bounded things, I would imagine that, for example, the clock for our ABS system is always going to say that we return a command saying whether to open or close the brakes. And that clock should be defined at the top level. That should be the top clock. Yeah, I think that I don't know. The clock system always seems a bit. It seems too expressive, like for the kind of programs that we want to write. I have a feeling that there's a more restricted clock system somewhere in the ether that would work and would be easier for proving things.
Interesting.
I guess if well, I can show. I think I'll show a very, very simple example of it actually doing something. So here I have definition of a count when, which takes a predicate P, which is a stream of bools, and returns a stream of ints. And it says, given a recursive count, it returns the value of 0 followed by the previous count. So this is delay combined with initialization. So if there is a previous count, it's that, otherwise it's 0. And then you add, if the predicate is true, we add 1. If it's false, we add 0. So the syntax is weird, but you can compose them together at least. And then we write a property which says that if you count when false is always 0. Well, okay, don't prove that. Count when false should be 0, and that should be less than count when E for any expression E, and that should be less than or equal to count when true. And we can prove it inductively, and it dumps a bunch of stuff, but it works. It works for very simple things. And similarly, we can generate C code for it by taking the same definition and instantiating these reset and step functions. We get C code that, so the reset function just sets the states to 0. And the step function does the actual work. So the current implementation of imperative code generation introduces a lot of duplicate work because it's just, it was the quickest thing I could implement to get it working end to end. And the microcontrollers that are running these things are actually pretty powerful. So it doesn't matter for these simple things.
That's really cool to see. My question was kind of related to what you were showing. So, so you're writing F-star terms against your against this applicative functor API, and then you say you have 2 translations. You're translating this thing to a label transition system as well as to LowStar.
Yeah, exactly.
And it sounds like you're operating at the meta level for those translations. You're writing tactics to transform F-star terms into either LowStar or to this LTS.
So the definition of the translation is actually just straightforward F-star, but then I have some very simple tactics. Well, I mean, the tactics just call normalization. Really just call NBA.
Could you give us could you show a little snippet of the translation to the LTS?
Yeah, absolutely. So I got this. Okay, so this module system base defines the LTS, which says it takes an input and a state and a result type, and it has a init predicate, which takes a state and returns a property. And it has a step predicate, which takes a concrete input and the state it started at and the new state and the result. So the language that I showed is deterministic, assuming it's well formed. So we could express it simpler as a simple one that returns the new state and returns the value. But I want to have contracts. I want to be able to generalize over approximate functions by their contracts, and for that I need to express it as a relation rather than a function. So for a simple map is probably a good example, right? So if we take a system, if we have a function f from value 1 to result, and we have a system that returns value 1s, we can translate it to a system that returns results. And it's relatively straightforward. It needs some quantifiers, which is a shame, but it's okay. And then I have separately, I found that defining the systems separately from the recursive function that actually translates them was easier to prove certain things. But I don't actually call system map. Okay. So if you have a bound variable, a De Broglie index, then you get the input. The input is a tuple of all the bound variables. Get that input tuple and map it with this index function to index into the tuple. So it's pure total F star. And we can prove some things about it, but I've commented all of the proofs out while I'm updating things. But then when we check it, we call this system of exp, and then we just, the key is to use this NBE tactic here, which just very simple. So that ensures, well, I think it could be tightened up, but I hope that there will be a way to ensure that the translation function is just fully evaluated away.
That's really cool. Wow.
Yeah, I'm really
So you think that most of your proofs can be done but in this style, just with TAC and BE?
I'm actually not sure. So this is very similar to the method of proofs that the model checker we were using, Kind2, uses. So Kind2 uses k-induction, which okay, so one induction says that assume the thing holds for one step and then show it holds in the next step. K-induction says assume it holds for k steps and then show it holds in the next step. So the really cool thing about this is that it gives you extra context about the system you're trying to prove without requiring you to come up with extra invariants manually. So we found that we were able to prove a lot of things without Kind2's extra invariant generation machinery. Like, we had accidentally turned off the invariant generation, so we were just using simple k-induction, and it's very effective. So I hope that we will be able to use I think that I can extend this with k-induction, and it'll require manually finding the right k, but I think it will be relatively effective. But yeah, I guess one of the things I'm really excited about is that when Kind2 got stuck, there was no real way to make progress. Like, it either proves the thing or it doesn't, and you can't say apply this lemma or whatever. So what excites me is having a bit more control there. I think that if we could prove things manually and compose them a bit better, that'd be nice.
Really great. Would you mind saying a little bit about how, I mean, I'm looking at this stuff and like, you've done a lot. How did you get going? There isn't that much documentation about F-star. I mean, you've figured out a bunch of things.
Oh, right. I guess, I mean, a lot of it feels very similar, very familiar, just from Coq and from doing a little bit of Agda and stuff like that. So yeah, it's, yes, I've had to dig into the implementation of the compiler a bit. Like, I saw a issue earlier today which had a grammar of the language, and I thought that would have been useful because I've had to go into the parser and look at the grammar in the parser to figure out what some things were. So, but the implementation is pretty nice. So, so I haven't had too much trouble there. Yes. Yeah, it's funny. I find it really interesting because sometimes, a lot of the time, I'm really impressed with the things that the machinery here can prove. I mean that F-Star's machinery can prove automatically, like things that I would have naively thought required extra inductive hypotheses, extra inductive lemmas. Sometimes it can just get it, and it's quite amazing. But sometimes it's confusing. What did I need to? I needed to prove a strange lemma today, but I can't remember what it was. But yeah, I'm really impressed. I think that we were also using at the self-driving car company, we were also using Frama C a bit to verify some C code, and it was relatively good. Like people with cock experience could prove things in Frama C. I don't think none of the non-cock people would have been able to prove anything in Frama C really, but if I had known about F-Star back then, I think we should have just used that. It would have done resolved a lot of the problems that we had with pharmacy.
It's interesting to hear you say that. I'd kind of qualify that with, it seems to me that what you're doing here is like you're working at a higher level of abstraction where you're not writing LowStar by hand, right? You're generating LowStar from this DSL, and you have probably have some structured way of arranging the LowStar proof.
Yeah, that's a good point. So I haven't actually tried writing any LowStar programs in Anger. I guess, yeah, I was thinking of it from a different application, like this for control systems, but we still need drivers and things like that implemented that were the things we couldn't write in Lustre, we wrote in C, and probably those things we could have written in F-Star. We looked at gosh, what's it called? Y3. Y3 has a extraction to C code, but it's doesn't seem, I didn't think it was very well defined, and it doesn't have the normalization that F-Star seems like it would make writing LowStar a lot more pleasant.
Okay, so yeah, I think we're at the end of the hour. Thanks, Amos, again. Thanks for the interesting talk. And thanks to everyone for joining, especially those who joined like at the far end of the day, far ends of the day. So thanks again. Bye.
Yeah, from in the so early in the morning.
Thanks, Amos.
Bye.
Thank you.
Great to meet you all as well.
Great talk. Thank you.
Oh,